let's switch the order up slightly and do the review of things first. And then while we're reviewing what all the relationships are, we will talk about the units simultaneously. Okay. So magnetomotive force, MMF. Okay. So this is analogous to voltage in an electrical circuit. So this is the quantity that's driving flux around the magnetic structure. Our MMF is equal to N times I. So this is just the total current. N is the number of turns. Current is in amperes. So this is in amp turns. So that is the unit of MMF. This will also be equal to H times L, where H is the magnetic field strength measured in amps. And I'm going to put in parentheses here turns, because if there's a coil, there will be some number of turns and it's a measure of the total current. So amp turns per meter. And this L here is the average path or average flux path, let's call it that. And so it's just the average distance the magnetic flux travels, measured in meters. Our magnetic field strength, there's going to be our magnetic flux density B, is equal to the magnetic flux divided by the area. So let's write this stuff down. So this is flux density, which is measured in Tesla, where a Tesla is a Weber per meter squared. Phi B here is the flux measured in Webers. And the area here, or A is for the area, and it is measured in meters squared. Okay. So now let's look at kind of Ohm's law for magnetic circuits. So Ohm's law for magnetic circuits is Ni is equal to, flux times reluctance. Okay. So once again, this is our magnetomotive force, MMF, measured in amp turns. Phi B is still our flux measured in Webers. And so R here is our reluctance measured in amp turns per Weber. You might also see it as amps per Weber or rels. Rels is a really, really old unit of reluctance that doesn't actually mean anything anymore. But if you look at a 40-year-old textbook like I do sometimes, you might see rels in it. Okay. So from this, we could say that our reluctance, R, or funny looking R, is Ni, our MMF, divided by our magnetic flux. Another way to look at this is that it is the length divided by mu times A. So this length here is the average flux path that we talked about earlier. Measured in meters. Mu is the permeability. Measured in henries per meter. And A is the area. Measured in meters squared. So if we look at this, or these units here for these different quantities, what we'll find is that we have meters per Henry per meter times meters squared. So that's going to look like meters per Henry meters, or 1 over a Henry, right? Well, since a Henry is equal to let's see, Henry's is amps, seconds. No, excuse me. Trying to remember, give me a second here. L so voltage is equal to Henry's times amps per second. So a Henry is a volt second per ampere. Sorry if I did do that out. So 1 over a Henry is going to look like an amp per volt second. So now we have to relate Webers to voltage. Give me a moment to remember how to do that. All right, let's just give it a Google. Where is my mouse thingy? There we go. Let's see what good old Wikipedia has to say here. So Weber is a volt second. Right here, the third relationship. So if a Weber is 1 volt second, then a Henry is a Weber per ampere, and the inverse of a Henry would be an ampere per Weber, which is effectively what our reluctance unit is. So there's lots of little bitty dumb relationships buried in there, but I think we've got all of them written down on the same page now. Okay. All right, so let's see, I'm not ready to talk about flux linkage just yet. And so therefore I'm not ready to talk about inductance just yet. So I think that is pretty much the gist of all of the different relationships and how they're related to each other that we will be dealing with. All right, so before we talk about new stuff, specifically meaning magnetic circuits that contain an air gap, let's look at an example problem. Okay. So this is very similar to the structure that I asked you guys to find the equivalent reluctance of on Tuesday, except that I'm putting my coil on a different leg of the structure. Okay. So I think I've been drawing the physical structures in blue, so I'll continue to do that. So this is what we're going to be looking at. A cinder block-like shape. And let's define some dimensions for this thing. So I'm going to call its dimension in this direction L1. And let's say that L1 is 80 centimeters. Let's call this dimension L2, where L2 will be 50 centimeters. Let's call this dimension W1. We'll also call this guy right here W1, where W1 is 10 centimeters. Let's call this dimension W2. This will also have the same width, as will this piece right here. So effectively, all of the vertical beams have the same width and all of the horizontal beams have the same width, but those two widths are different things. Let's say that W2 is 8 centimeters. And our thickness, T, is equal to 10 centimeters. And our coil is going to be wrapped around this middle leg or this middle beam. Okay. Where our current I will be flowing in the indicated directions and our coil has N turns. Okay. So let me ask you guys a question here. Do you think that the equivalent reluctance of this magnetic structure would be different if I put the coil on a different leg? Yeah, because the flux will take a different path. And the equivalent reluctance is simply going to be the ratio of the MMF that's driving the flux around our magnetic circuit divided by the amount of flux. So putting the coil in a different place is going to cause a different amount of flux to flow. It's going to look like a different combination of reluctances effectively. Okay. All right, so I am going to look at this structure as if it were an electrical circuit effectively. Okay. So I'm going to start with that middle area where my coil is. And so I'm going to see the reluctance of the middle. And I'm going to put that in series with my MMF. So that's the middle branch. Now let's look at the left branch. So effectively, I'm saying, what if my flux goes through here? And then what does my flux see as it flows around this path, right? So I'm going to see some reluctance here at the top left. So let's call this RTL for top left. Then let's call this guy over here just R left. Oops, shouldn't draw that one yet. And let's call this one here RBL for the bottom left path. Okay. Now, actually, we'll finish drawing the magnetic circuit or equivalent magnetic circuit, and then we'll talk about a couple of things here. Now let's talk about what the right path is going to see, right? So our flux is being driven up through that middle branch, and it can flow to the left, but some portion of it can branch off and flow to the right. So we're going to have this bit, and then this bit, and then this bit, and then the flux that is branched off to the sides comes back together and flows up, just like we would expect current to do in an electrical circuit. So from that, I'm going to have this reluctance, which is in the top right, this reluctance, which is to the right, and this reluctance, which is in the bottom right. Okay. All right, so a couple of things here. We don't know how much MMF we have. We don't know how much flux we have. We only know the geometry of the system, okay? So we are trying to see effectively the equivalent resistance or the equivalent reluctance that is connected to our MMF source. So what we can do is just take the MMF source out and look in through those terminals and figure out what the equivalent resistance looks like, okay? So what I'm suggesting is that we do something like this. And we're going to find the equivalent reluctance seen between these terminals, which I'm arbitrarily labeling A and B, right? So we've turned this problem into a resistor combination problem, okay? Let me write down all of my names here: RTL, RTR, R left, R bottom left, R bottom right, R right, and R mid. Okay. Our reluctance of each one of these pieces, so in general, our reluctance is going to be given by the length divided by the permeability multiplied by the area. And that is one thing that I did not tell you guys, so I'll go ahead and put that in right now. Sorry, I forgot to do it. The permeability of the core, which is required for us to know, is going to be 5,000 times stronger than the permeability of free space. Okay. Free space, or the permeability of a vacuum. So mu naught is a constant of the universe that tells us the permeability of a vacuum, and all materials are measured relative to that level. So ferromagnetic materials, and we discussed this to some extent on Tuesday, have a permeability that is much, much larger than that of free space. So because the permeability of our core is 5,000 times larger than that of free space, it's pretty safe to assume that this is a ferromagnetic material making up our core. C for core. Yep. All right, so which of these, let's count these up. 7 different reluctances do you guys want to calculate first? R left. Okay. So R left is going to be the length the flux travels as it travels down that left-hand beam. So the average path the flux takes divided by the permeability of the left-hand portion of the core, which, since this is all just one material, that's just going to be mu c, divided by the area that the flux sees. Okay. So the average path of the flux, let me do this in purple here. Let's put it as left. Is going to be this distance, right? We did something like this symbolically in class on Tuesday, okay? So this distance L left is just going to be L2 minus W1. Okay. Everybody okay with that? We'll throw numbers in here in a moment. Then we have our permeability. So what is the area that we see as the flux travels down this leg? So that area is going to be the size of this rectangle here, or this cross-sectional area of this leftmost leg, okay? So it has, the leftmost leg has a width of W2 and a thickness of T. So the area is simply W2 times T. So now let's throw some numbers in here. Actually, let me come down so I make sure I have enough room. So we are going to have L2, which was given as 50 centimeters, minus W1, which was 10 centimeters, divided by mu c, which is 5,000 mu naught, where mu naught is 4 pi times 10 to the negative 9 henries per centimeter, times W2, which is 8 centimeters, times our thickness, which is 10 centimeters. And if we look at our units, we are going to have centimeters over henries times centimeters. Yes, Shaw? 5,000. Nope. By all means, if you think I'm making a mistake somewhere, please let me know. So thank you for that. So we're going to wind up having centimeters divided by henries times centimeters if we look at the units here. And as we figured out a little while ago, a henry is a Weber per ampere. So when we flip that over, we're going to have amperes per Weber, or amp turns per Weber, as our unit. if we put these numbers in our calculator, what we will find is that we'll have 7.958 times 10 to the 3 amp turns per Weber of reluctance along that left-hand beam. Everybody okay with that? Anybody got any questions, comments, concerns? All right, so now let's look at things really quickly here, right? Because we have 7 of these things to figure out. Is the size of the middle any different than the size of the left hand? Nope. What about the right hand beam? No. So the middle reluctance and the right hand reluctance are both going to be the same thing as the left hand reluctance, right? So we can say that R mid will be equal to R right, which would be equal to R left, which we know to be, 7.958 times 10 to the 3 amp turns per Weber. All right. So we know 3 of our 7. Somebody tell me the next one that we want to look at. Yes, ma'am. How did I say that they're equal? Okay. So the length that the flux is traveling is the same, right? So if I extend this purple line thing right here all the way across, this is the distance the flux travels when it goes through the middle path, which is the exact same as the distance the flux travels when it goes through the left-hand path. This is the distance the flux travels along the right-hand path, which is the exact same as what it traveled in the middle and on the left-hand side. So the length the flux travels in the middle and the right-hand path is the same as the left. But that's not enough for them to be equal. They also have to have the same cross-sectional area, right? So the size of this rectangle has to be the same as well. Since all of the vertical members have a width of W2 and the whole thing has a thickness of T, they all have the same cross-sectional area of W2 times T. So because they have the same flux path and the same cross-sectional area, and they're made of the same material, the reluctance has to be the same. Okay, circling back around. Which of the 4 that we have left do we want to deal with next? Top left, all right. So this is going to be the length in the top left path divided by the permeability of the core multiplied by the area seen as the flux travels through that top left path. So let's scroll up here a little bit. Let me use a different color because this is getting real busy. So let's use pink. So this distance is the distance traveled by the flux as it goes through the top left path. Okay. How do you think that's going to relate to the distances that we're given for the geometry of the system? So 1/2 L1 minus W2. Yes, that's correct. Then we have our core permeability, and now we have to find the area that the flux is passing through. which is going to be the area of this pink rectangle here. So it has a width of W1 and a thickness of T. So the area will be W1 times T. So let's throw some numbers in here. We are going to have 1/2 times L1, which was 80 centimeters, minus W2, which was 8 centimeters, divided by 5,000 times 4 pi times 10 to the minus 9 henries per centimeter, times W1, which was 10 centimeters, times our thickness, which was 10 centimeters. Our units are going to work out to be centimeters divided by henries times centimeters, or 1/henries, which is an amp turn per Weber. And if we plug our numbers in, we get 5.093 times 10 to the 3 amp turns per Weber. Are we all okay with that calculation? Everything seems groovy? Great. So now let's look at the other things, right? So here is our length LTR. It should be the exact same thing as LTL, where we're assuming that the middle beam is exactly in the middle of our structure, right? So the flux path length is the same. The cross-sectional area will be the same, and the permeability is the same. So this section of our structure, RTR, should be the same as RTL. And we could apply the exact same logic to our bottom paths as well. And we would find that R top right will be equal to R bottom left, will be equal to R bottom right, will be equal to what we found for the top left. And so all of these are 5.093 times 10 to the third amp turns per Weber. Is everybody okay with that? So we now know all 7 of our reluctances. So now we just need to do reluctance combination. And reluctance combination is going to work exactly the same as resistance combination. So how are we going to do that? I mean, technically, yes, we are going to use that. I absolutely hate that particular way of doing it. So I'm going to show you guys something different, because that just annoys the shit out of me, if I'm being entirely honest. So let's look at a couple of things here real quick, right? You guys know how to identify nodes and all that kind of good stuff. So we could call this a node, 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 and this a node, right? So how are the reluctances RTL, R left, and RBL connected based on what the nodes tell us? They're all in series, right? So we could replace all 3 of those with a single reluctance, which I'm going to call RL prime, where that would just be RTL plus R left plus RBL, right? Sorry, I went slightly too far. So RL prime will be RTL plus R left plus RBL. And that will have some numerical value, which I didn't bother figuring out. We'll talk about that in a second, right? We could do something similar for the right-hand side. So we can call this one R prime, where that's going to be RTR in series with R right in series with RBR. Is everybody okay with that? So how are those two things going to compare to each other? They will be exactly equal. Okay. So whatever it is, they're going to be exactly equal. All right. So give me just a second here. Allison, that's you, right? Yes. So Allison said that we have resistors in parallel or reluctances in parallel. And so we're going to combine them using that 1 over R1 plus 1 over R2, and then we take the reciprocal of the whole thing. And I said very emphatically that I freaking hate that, because I do. So perhaps you guys have seen this before. If not, I'm going to show you something new here. If we have two resistances in parallel, so let's call this guy R1 and R2, and we're trying to find the equivalent resistance. The equation that you guys are familiar with says that this should be 1 divided by 1 over R1 plus 1 over R2, right? This is the method that you guys, it seems like you were taught. What I'm going to do is I'm going to get real fancy here, and I'm going to multiply 1 over R1 by 1, but I'm going to express 1 as R2 over R2. Anybody have a problem with that? I'm going to multiply 1 over R2 by R1 over R1. And so what that allows me to do is combine some things, right? So I'm going to have R1 divided by R1 times R2, and I'm going to have R2 divided by R1 times R2. And because the denominators of my denominators have the same denominator, I know that's a whole bunch of crap there, I can combine those fractions together. And so that's going to give me 1 over R1 plus R2 divided by R1 times R2. And when I have 1 over a fraction, it's the same as just the reciprocal of the fraction, giving me R1 times R2 over R1 plus R2. So you will never see me do that reciprocal thing when there are two resistances or two reluctances or whatever. I will always do this R1 times R2 over R1 plus R2 because it's less buttons on my calculator and I'm very lazy. Okay. This only works for two reluctances or two resistances. I want to be very, very clear about that. So you can't use it for 3 or more, but for 2, in my opinion, this is the fastest and most efficient way to perform this calculation. So now you guys know it as well. Let's take this one slight step further here, because we have a special case that we are about to deal with. We have two equal reluctances or resistances in parallel, okay? So we know that Req should be R times R over R plus R, because all of our resistances or reluctances are the same. This comes out to be R squared over 2R, or just 1/2 R. So whenever we have two identical things in parallel, the equivalent is just half of what we started with. So putting all of that together, what should our equivalent reluctance be for this structure that we see here? It should be R middle plus 1/2 the reluctance of one of the legs. And if we use the numbers that we got earlier, this is going to come out to be 1.703 times 10 to the 4 amps per, or excuse me, amp turns per Weber. Does anybody have any questions about that example problem? Yeah, if they're both identical, then you only care about one side because the other side is the exact same thing. So we identified 7 different reluctances because there are 7 different paths the flux will take as it travels through this magnetic circuit. But we only performed really 2 calculations because all of the other paths are identical because the flux traveled the same length and passed through the same cross-sectional areas. So if I gave you like the wrong stylus here. So if I gave you something like this on an exam, let's call this W. This will also be W. This guy is W. This guy is W. This is our length. But this is also the same exact length. And then let's throw a coil in here. Here's I, here's N. You would actually only need to calculate one reluctance because all of the paths are of the same exact length and they all see the same cross-sectional area and the core is made of one material. Another way that you could think about it is you could just find the total flux length, which is just going to be 4 times the length of each leg, and then use that to calculate the equivalent reluctance from there. So use symmetry and things like that to make your life easier, because doing the same calculation, in this case, it would have been 4 times. I mean, it's correct, but geez, it takes too damn long to get the same result, right? So if you can exploit the symmetry because the lengths are the same, the cross-sectional areas are the same and things like that, use that to cut down the time it takes for you to perform these. All right. Any other questions or anything about this before we throw an air gap in here and mess things up a little bit? All righty. So this is the last thing that I'm going to talk about today, and I'm going to work another example problem, and then I'm going to let you guys do things. Air gaps in magnetic circuits, okay? So there are some magnetic circuits which are going to have moving parts. Electromechanical relays, motors, generators, things like that, all involve movement. And so, because you're expecting movement inside of your magnetic circuit, you will see air gaps occur. So consider the following core here. Where I am vastly exaggerating the size of an air gap that you would see in an actual magnetic circuit. Wrap a coil around one leg of this bad boy. So based on the direction of the current, which I didn't label the current I, so let me do that here real quick. So based on the direction of the current, we should see that our magnetic flux travels up to the right and then down, and then it's going to hit our air gap. And because the flux has to form closed loops, over here in the core, it's going to flow down to the left and then back up. So what's going to happen in the air gap is something like this. Okay. So this fancy looking squiggle thing here just means I'm looking at just the part where the air gap exists, and I'm not concerned too much with the rest of the core, right? So straight down the middle, we're going to see that our flux travels in a straight line. But off to the side a little bit, we're going to see that it starts to spread out. Like so. Okay. So the reason why the flux is spreading out like that is because the relative permittivity of the air that the flux is traveling through is much, much smaller than the permeability. The permeability of the air that the flux is traveling through is much, much smaller than the permeability of the core. So since you don't have a very high permeability core material, confining the flux into a small space, it will spread out in the air. So we have a certain gap length here, LG, that the flux is traveling. but we also have a certain cross-sectional area, okay? So this area right here is the area of the core, defined by the width of the core and the thickness of the core at that point, right? Well, the flux that's traveling through that air gap sees a much larger area, okay? So what we are going to do is we are going to consider that the area of the air gap will be the thickness of our core plus the length of the air gap times the width of our core plus the length of the air gap. And now we can consider our air gap as just another reluctance in the flux path. Okay, so we're going to see that our air gap contributes some reluctance R sub G that is in series with whatever reluctance the core has. So let's take that idea and work another example problem. So this is going to be our structure, okay? This is what a electromechanical actuator or a electromechanical relay might look like to some extent, okay? Let's call this length L2. This width W. Let's call this length L1. This width will also be W. This width will also be W. This width will also be W. And this length will also be L2. I'm going to draw my winding. I flowing in, I flowing out. Our coil has N turns. And let's give us some numbers to look at. Okay. So let's say that L1 is 8 centimeters. L2 is 4 centimeters. Oh, and I didn't define this, so my apologies. The length of our air gap will be LG. Will be 0.5 millimeter. So we should see that the length of our air gap, or the distance that our air gap occupies, will hopefully be smaller than the dimensions of our magnetic circuit usually. If we don't have that, we're going to lose a lot of flux. Okay, so if we want to minimize core losses, which we'll talk about on Tuesday, we want our air gaps to be very small. Let's say that our width is 1 centimeter and our, thickness, T, is also 1 centimeter. And so I don't forget, our core has a permeability that is 1,000 times greater than free space. And this particular circuit is sustaining a flux of 100 microwebers in the core. Okay. For a real electromechanical relay, we would actually see this rightmost plate would be mounted kind of on a spring, so that when we pass current through it, it's going to create a flux that will attract that bar to move over and close our contacts. Anyway, all right, so what would our equivalent magnetic circuit for this be? Somebody want to come up here and draw it, or you want me to do it? Okay, I'll do it. You guys are terrified to do it in front of people. All right, that's okay. We'll break you of that habit. So I'm going to do very similar to what I did for the last problem. I'm just going to break this up into little parts. In the faculty meeting yesterday, Dr. Hall said he was having his students get up on the board and write stuff. I was like, I'll give that a whirl. And then you guys said no. That's okay.
That's a new thing. I've never done that before.
Okay. So what I've done here is I've just associated a reluctance with each of the parts of the structure, and then also a reluctance with each of the air gaps that the flux is going to see as it travels around its clockwise path in this magnetic circuit, okay? So our left is the leftmost vertical beam, our right is the rightmost beam, our top is the top beam, our bottom is the bottom beam, and then we see two identical air gaps, and they are placed in series where it looks like they should go. Okay, nothing particularly wild or crazy there. Because all parts of the beams have the same width and all of them have the same thickness, they're all going to have the same areas, but there are two different lengths involved, which means we're going to have to calculate effectively two different reluctances for our core structure, and then one reluctance for our air gaps, and then put it all together, okay? So let's do the left one first, okay? So what is the length that my flux travels along that leftmost beam? L2 minus W, that's correct. Because the beam is part of the core, we'll have mu C. What's the area that our flux sees as it travels on the left path? W times T. So we can throw numbers into this. So this is going to look like 4 centimeters minus 1 centimeter divided by 1,000 times 4 pi times 10 to the minus 9 henries per centimeter, excuse me. And then 1 times 1 is 1, and so I'm just going to call this 1 centimeter squared. If I put this in my calculator, I get 2.387 times 10 to the 5 amp turns per Weber. Calculation is effectively exactly like we did for the last example problem. It's just got different dimensions, right? So anybody have a problem with where any of these numbers came from? All right. Since the left-hand part of the path and the rightmost part of the path are the same length, the core material has the same dimensions, and the same permeability, I'm sorry. We can say pretty easily that R right will be R left. And so this is going to be 2.387 times 10 to the 5 amp turns per meter. Turns per Weber, excuse me. One thing that I just realized that I didn't do is ask you guys what we're actually solving for. We're trying to find, don't know why the screen keeps wiggling, it's driving me bananas. The MMF that's driving this particular amount of flux around our circuit. Okay, so that's our ultimate goal there. Sorry for not telling you that 3 minutes ago when we started this thing. All right. What about the bottom path? What's the length that my flux travels? L1 minus W. So this one is actually kind of a little bit tricky, so I want to talk about it here, okay? So the reason why I say that it's tricky is we're looking about the average thing here, right? So this length right here is going to be L1 minus 1/2 W, right? But we also have this little bit right here that is going to be one-half of a W, right? So what happens when we add those two things together? It's L1. I realize now that I made a mistake when I solved this, but that's okay. Then we're going to have mu C times WT. Let me wrap my head around this, right? So we have a distance of L1 minus 1/2 of a W, because that's the average length there. And then we have another 1/2 of W. So yeah, it's just L1. Okay. So L1 was given as 8 centimeters, I believe. And then we have 1,000 times 4 pi times 10 to the minus 9 henries per centimeter. Our area will be 1 centimeter squared. And so this is going to give us a number that I don't have written down because I did the calculation slightly wrong. So what I'm going to do, I'm going to get my calculator out here.
6.366 times.
So that seems pretty reasonable to me. So Jules says it's 6.36. So the number that I got was 5.57 times 10 to the 5 amps per Weber. How I'm going to fix this is because I subtracted 1 in my numerator. I'm just going to multiply this fraction by 8/7, and that'll fix it, right? So 5.57 times 8/7 gives me 6.366. Times 10 to the 5 amp turns per Weber. It sounded like there was some discussion amongst you guys. I'm happy for that. Is there anything that I need to address better? So
what I was saying
That is absolutely correct. Because the air gap has a different permeability and a different cross-sectional area, we are going to have to calculate that separately. So the total length that the flux path takes along that topmost path is going to be L1 minus half of a W plus the length of the gap plus half of a W. But because we're only interested in its behavior in the core material there, that's why we're leaving out that air gap contribution, and that's going to be the next thing that we calculate. Does that make sense? Good deal.
That doesn't match up at all. Like, I guess like it doesn't. The is the right word, but it's literally just the same.
So
Going to that air gap.
So the flux is being generated by the coil, right? So the coil is providing some amount of magnetomotive force, which is establishing the flux and pushing it through the path. Because magnetic fields formed closed loops, whatever flux is generated by the coil is the flux that's traveling around the whole circuit. Now, in the air gap, we will see that the flux will spread out some, so that the strength of the magnetic flux density is going to decrease, right? But the flux is going to remain constant throughout the circuit. Now, we are saying that because we are dealing with an idealized view of this. What we're going to talk about on next Tuesday will include the possibility that we have what are called core losses. So core losses involve the fact that we are passing current through this coil. We're causing flux to flow through the coil. That flux is going to induce currents in the material, which are going to cause the core material to heat up. That heat is going to generate some core losses. We can also have losses because we lose flux into the air in a gap, but we are not quite there yet. So you're 100% right that in a real system, it's not going to behave perfectly like this, but let's figure out how the ideal things work before we start breaking everything. Yeah. All right, so we have our bottom. The bottom is going to be the same as the top because it has the same dimensions and all that kind of good stuff. And now we come to, let me write this down, 6.366 times 10 to the 5 amp turns per Weber. And now we come to our gap. Okay. So we're going to use our same generic equation for calculating the reluctance, the length the flux travels, which in this case is going to be Lg, divided by the permeability. So what's the permeability of the gap going to be? Yeah, so just mu naught. Really, it would be the permeability of air, but that's so close to the permeability of free space, we're just going to leave it alone. We're not going to worry about that 1,000th of an increase or something like that. And then we have to deal with our area, right? So because we have an air gap, we're not just going to use our core cross-sectional area of W times T. The general rule of thumb is to increase the lateral dimensions of our core air gap by one gap distance. So that means we're going to increase the width by Lg and the thickness by a factor of Lg. So this is going to look like 0.05 centimeters, where I've converted half a millimeter into a 20th of a centimeter so that my units work out nicely. Mu naught is 4 pi times 10 to the minus 9 henries per centimeter. My width will now be 1.05 centimeters. My thickness will now be 1.05 centimeters. And when I throw all of this into my calculator, I get 3.609 times 10 to the 6th amp turns per Weber. So let me ask you guys a question. Is the reluctance of the air gap larger or smaller than the reluctance of the sections of core? Larger by a factor of about 10, okay? It's only a little bit larger, and this is again a factor of about 10 because the permeability of our core is only 1,000 times mu naught, right? If we had a very, very high permeability core, on the order of 50,000 or something like that, we would see that the air gap almost entirely dominates the reluctance of our system. To such a point that when we're dealing with very high permeability materials, the only reluctance that we actually need to keep track of is the reluctance of the air gaps, okay? You could treat the core material as if it had an infinite permeability and it really wouldn't mess up the math too terribly. So anyway. Our equivalent reluctance is going to be simply twice our left plus our bottom plus our gap. Since our right is the same as our left, our top is the same as our bottom, and we have two air gaps, and I'm going to have to calculate this really quickly. .98686. I'm going to call it 9 just to be argumentative. Times 10 to the 6th amp turns per Weber. So just really quickly here. So let's see, 3.609 times 2 divided by, oh, damn it. .969 times 100. So about 80.5% of the total reluctance seen by our flux is due to the air gap. So less than 20% is caused by the core material in this case because it has a relatively low permeability. If our core material's permeability were higher, we would see that that fraction of reluctance, total reluctance caused by the air gap would go up. All right, so we've done a whole hell of a lot of work here to figure out what our equivalent reluctance of our circuit is. How do we find our MMF? So let's go back to those first equations. Right. So this guy right here is Ohm's law for magnetic circuits. We are trying to find MMF, which is effectively V. We were given flux, which is effectively I, and we just found R. So since V is equal to I times R, MMF is equal to flux times R. So finally, I will be done talking for the day. I'm drawing the wrong damn symbol. So I'm going to call this MMF. I might also write it as N times I. They're all the exact same thing. Is going to be our flux phi B times REQ. So that should be 896.9. Yep. Alrighty, so that's what I wanted to talk about for today. Hopefully this is, I guess, a little bit closer to what you guys are used to. I'm not just a jackass up here doing all my math with symbols and no numbers. I'm going to try to do a nice blend of the two. So yeah, so I have your in-class assignment up here as well. I've also posted PDF copies of it on the course's Moodle page. And I also have created the submission portal link thingies on Moodle as well, so that you guys can turn in your digital copies if you want to do that, or the paper copies to me, whatever